Section 1 Introduction. We're going to talk about large language models, or LLMs, which have become a big deal in the field of natural language processing, NLP. Initially, these models were used for transfer learning, but now they're seen as a kind of all-knowing oracle. Interestingly, these models, which were trained to predict the next word in a sentence, can also provide accurate facts about the world. This has led to people viewing them as an alternative to search engines. However, despite their impressive capabilities, these models still make mistakes due to a mismatch between their training objective and the need for factual accuracy. Researchers have proposed several solutions to address the issue of inaccurate outputs from LLMs. One such solution is model editing, which involves tweaking the parameters of an LLM based on specific facts that need to be corrected. This approach aims to ensure the stability of other factual outputs after editing, enable batch editing, and make the editing process computationally efficient. In this paper, we question the whole concept of model editing. We raise concerns about its intended use cases, scalability, potential for bias, safety, and overall accountability. Instead, we suggest using models with explicit knowledge modules for tasks that require factual knowledge. We also recommend other existing techniques to reduce the need for model editing. However, we do acknowledge that direct editing can be useful in certain scenarios, such as interpretability probes. The idea of updating large machine learning models to meet local performance expectations was first introduced by Newsight. They highlighted cases where mistakes could have serious consequences, such as object detection in self-driving cars. Later research suggested that model editing could help protect privacy, eliminate bias, and keep up with time-sensitive facts. It was also seen as a way to understand the workings of complex models. Several properties of editing methods were identified, including reliability, locality, and efficiency. Later research added generality, consistency, and frugality. One of the main challenges in model editing is avoiding catastrophic forgetting, which is when an edited model performs poorly on tasks it was originally trained for. Various methods have been developed to address this issue, from editable training to changing specific parameters within models. The perception that LLMs can serve as knowledge repositories was first supported by the Llama benchmark. This involved querying pre-trained language models against a large number of knowledge triplets. However, this approach was found to have limitations, and more realistic benchmarks and robust querying techniques have since been introduced. Despite these advancements, LLMs still struggle with facts concerning rare entities. Their ability to answer a question depends on how often relevant information appears in the pre-training data. Therefore, they can't reliably answer queries about rarely mentioned facts. To be considered as fact repositories, LLMs need to be able to edit knowledge, maintain logical consistency, reason, and provide explanations. Current LLMs fail to meet these requirements. In conclusion, the evidence supporting the use of LLMs as fact repositories is weak. We will now focus on specific arguments regarding the capability to edit models as if they were fact repositories. Section Summary. Large language models, LLMs, have gained popularity as all-knowing oracles, capable of completing factual information. However, there is an inherent mismatch between their pre-training objective and the desire for factuality. Model editing, which involves tweaking parameters inside an LLM based on individual facts, has been proposed as a solution. However, we question the idea of model editing due to concerns about intended use cases, scalability, bias, safety, and accountability. Instead, we advocate for models with explicit knowledge modules and other techniques to mitigate the need for model editing, except for specific scenarios like interpretability probes. Section 3.2 Systemic Mismatch. One fundamental characteristic of language learning models, LLMs, that sets them apart from their use as knowledge repositories is their unpredictable nature. This unpredictability can be beneficial in creative, exploratory, or free-form tasks like summarizing, where variation and surprise are welcome. However, in other scenarios, we might prefer models that provide a range of possible outputs, allowing us to gauge the likelihood of each response and adjust our expectations for a reliable result. Unfortunately, many models available through third-party APIs lack this feature, leaving us with text generated from an unknown distribution, which we believe is inadequate for tasks that rely heavily on factual accuracy. Interestingly, it could be argued that LLM's tendency to get facts wrong is not a flaw but a feature. Their primary training goal is to simulate plausible text continuation, so it's not surprising that they might repeat common misconceptions, undermining their use for factual purposes. For example, if most people mistakenly believe and write that Los Angeles is California's capital, an LLM is likely to complete a related prompt in the same way. LLMs also lack built-in reliability or consistency when generating outputs from a distribution. The same prompt can yield contradictory facts in different instances. Moreover, the notion of editing facts in a model implies that we always want a model to provide a fact in response to a question. However, some questions might be based on harmful assumptions or stereotypes. In such cases, we might prefer to eliminate such facts or equip the model to challenge the assumption, rather than providing an answer. Despite these issues, it's important to note that some facts are essential for basic communication. An LLM that can't confirm whether trees have leaves, or insists they don't, would be largely useless for tasks requiring interaction with the world. As we continue to explore these issues, we hope to find a balance between what an LLM must know and what it should not know. Estimates vary, but there are over 100 million significant facts in the world. Even defining what constitutes a fact is unclear. Does a minor change in demographic statistics or a new obscure sports record warrant an edit? What about the daily activities of world leaders, celebrities, or journalists? As new facts emerge and change daily in various fields, it's implausible to keep up with them all through surgical model editing. If we choose to limit the facts we deem important enough to edit, we introduce bias into the system, leading to potential harm. This bias can be both implicit and explicit and is incredibly difficult to avoid. The sheer volume and variability of facts can also lead to bias in evaluating the set of facts that remain unchanged after an edit. Even rephrased versions of edited facts may not change in line with the selected phrasing, nor may the facts that follow logically from them. This issue also poses a safety risk, as unchecked facts can turn out to be crucial for model usage but may be overlooked or not explicitly covered when designing a benchmark for evaluating the effects of edits. There's evidence that it's harder to edit out facts above a certain popularity threshold, measured in terms of views on Wikipedia articles, compared to less popular facts. As a result, less popular facts may be edited alongside target facts without being deemed important enough to check during testing. This could lead to a narrowing of the knowledge provided by LLMs, focusing on popular topics and interests while losing relevance in many areas that contribute to the diversity of human and natural experience. Empirical evidence suggests that existing editing models fail to account for the ripple effect of a fact editing operation. For instance, adding the fact, Jack Depp is Johnny Depp's son, introduces additional facts that the model needs to update, such as, Jack Depp is Lily Rose Depp's sibling. Symbolic approaches to this task have shown that this knowledge updating task is computationally complex, even nitrogen monophosphide hard, as seen in truth maintenance systems. These results apply to machine learning-based approaches as well. Therefore, there's a theoretical basis to conclude that model editing will at best address the problem of consistent updating in a roughly approximate manner, and most likely fail to update rarely seen facts within the ripple effect of editing operations. Recent empirical findings also reveal additional weaknesses of edit methods by extending the evaluation suites to cover aspects beyond fact editing metrics, such as specificity and robustness of the models post-editing. Section Summary. LLMs, despite their stochastic nature, are desirable for creative tasks and data exploration. However, relying on LLMs for factual applications is insufficient due to their tendency to generate incorrect information. The vastness and variability of facts make surgical model editing impractical, leading to biases and potential harm. Additionally, editing models fail to properly account for the ripple effect of fact editing, making consistent updating challenging. Section 4. Alternatives to model editing. We're going to discuss alternatives to model editing. Model editing is a technique used to control the output of language learning models, LLMs, to ensure they produce accurate and up-to-date information. If an LLM produces incorrect or outdated information, the idea is to remove that information from the model's memory and try again. However, there are other methods to improve the accuracy of LLMs, such as using reinforcement learning with human feedback or adding a fact-checking step to the training process. We'll now look at some alternatives that aim to achieve a more manageable goal than direct model editing. These methods don't assume that the LLM is a storehouse of facts, so they avoid the difficult task of updating this storehouse in a logically consistent way. While these alternatives have their own limitations, we believe they point towards more promising research directions. One such alternative is incorporating knowledge bases. In retrieval-based models, factual knowledge is stored in a separate component outside the LLM. This external fact store can take various forms, such as a collection of text documents, a graph, a set of vector embeddings, or even expert language models trained on specific datasets. The model can then cite the source of a specific piece of generated text, allowing the user to judge its credibility. Once the external knowledge is retrieved, it's combined with the LLM's generation process. Several methods have been proposed to integrate this external knowledge with the LLM. For example, one method uses a k-nearest neighbor approach with interpolation, while another combines the prompt with retrieved documents through a specialized cross-attention mechanism. Other variants include a fusion-in decoder method and TRIME, all of which maintain the capacity for few-shot in context learning. Recent research has focused on learning how to combine search engine results with the context provided to the LLM to answer a specific question. For instance, the SAIL method fine-tunes language generation based on search results and learns to select trustworthy sources. The Cook method combines multiple curated knowledge sources into a single system, where each source is modeled as an independent language model and an integrator LLM combines the information from these modules to answer a question. In all these methods, factual knowledge is stored outside the LLM and can be manipulated without retraining the model. These methods have proven to be scalable in terms of the number of facts they can handle. Updating the fact store is as simple as updating a database, which simplifies the task. However, these retrieval-based models don't solve all the problems associated with model editing. One issue is determining the origin of a piece of generated text in these combined models. The text could be determined by the LLM's internal parameters, the external stores, or a combination of both, even if they're not logically consistent with each other. Facts that the LLM encountered more often during training may carry more weight, even if they're incorrect or outdated. Another issue is that modifying knowledge in explicit memory module networks like Phi is not straightforward and requires changes in the LLM component as well. This was observed in a benchmark test called RealQA, which contains questions about time-sensitive data. The test showed that in many cases, GPT-3 correctly integrated data retrieved from a knowledge base and injected into the context, but often still generated text based on outdated data from the LLM. While separating the components and identifying the composition of external knowledge improves transparency, determining the origin of the generated text and controlling which sources are appropriate in a given context remains an open research question. Another alternative is continual training, which involves incrementally training a model by introducing new tasks or domains. This doesn't directly align with the goal of model editing, which is to update specific elements in the model while keeping tasks and domains unchanged. However, the risk of forgetting identified in continual learning is similar to the drawdown identified in model editing. In this approach, model editing could be seen as a type of retraining or post-training. However, just fine-tuning a model over a set of facts to update can degrade other facts. One solution is to apply techniques from continual training to the task of incrementally updating LLM knowledge. In conclusion, while continual training may seem to avoid the risks of model editing, it still faces many of the same evaluation problems. Section Summary. The section discusses alternatives to model editing for controlling the text generated by language models, LLMs, to improve factuality. These alternatives include incorporating knowledge bases, retrieval-based models that retrieve external factual knowledge, and continual training to incrementally update LLM knowledge. While these approaches have their own limitations, they offer promising research directions for improving LLM-generated text. Section: Concept Erasure. The aim of concept erasure is to eliminate any unwanted bias from the embeddings created by language learning models, LLMs, and consequently from the text they generate. This aim is driven by the desire for fairness, to ensure that certain protected attributes, such as gender, race, or age, do not influence the generation of text. This is somewhat similar to the goal of model editing, which is to prevent harmful content from being generated. However, there are some key differences. 1. Concept erasure deals with broad, well-recognized concepts, like the protected attributes mentioned earlier, rather than less clearly defined specific facts. 2. It functions as a transformation applied to the embeddings after they have been generated, rather than a modification of the model itself. This allows for greater accountability than a model that is constantly changing. 3. The effectiveness of concept erasure can be verified using well-established metrics within a predefined scope. Although concept erasure has a narrower scope than model editing, it sets a goal that can be measured in a reliable way using aggregated metrics. Future research could explore whether the concept erasure approach could be extended to address specific aspects of factuality, such as time relevance. Perhaps it would be better to have a model that is aware of its own limitations? As pointed out in a previous study, one way to prevent the generation of incorrect text is to identify what the model does not know. For example, can an open domain question answering system recognize when it cannot provide an answer? The issue of unanswerable questions has been tackled effectively. However, the challenge with LLMs and factuality is that problematic questions, like those mentioned in section, appear to be answerable.